All right, so this week the plan is to look at one section, okay, 6.5. We're going to do part 1 today, part 2 tomorrow. As I said in years past, I've done both parts in the same day, so really by splitting it in half, it's pretty short, pretty straightforward material, and the test on this will be on Wednesday. And I think overall people will find it easier than the graphing stuff we did last week, I think. All right, so what we're going to be looking at is what's called trig functions of acute triangles or acute angles. And it basically means we're going to be given a triangle, and we're going to have to find out how big the sides and how big the angles are. That's pretty much the goal. Now, we're always going to be working with a right triangle this week. So, someone remind me, what does that mean if you have a right angle? Nick?
One of the angles is 90.
Yeah, one of the angles is always going to be 90, and as long as you have a 90, there's a certain theorem you can always use that tells you a relationship about the sides. So, Nick just said a right triangle, again, is a triangle that has a 90-degree angle. What do you call the side that is opposite the 90? It has a special name. Yeah, Caleb?
That'd be the hypotenuse.
It's the hypotenuse. And what do we call the other two sides in general? Yeah?
Adjacent.
We're going to talk about those two terms. So, yeah, that is a term you can use. I'm thinking of a word that applies to both sides. The other two sides are called there's a word, and then you can be more specific about which side is which, and we'll get into that. Yeah?
The legs.
The legs. All right, so the side opposite the right angle is your hypotenuse. Two other sides are the legs. Okay, here's a diagram just kind of showing everything we just said. Generally, the letters that we use to represent the sides are A, B, and C. A and B are the two legs, and C is the hypotenuse. Remember that because you have a right angle, the other two angles have to be acute. What do all the angles add up to in a right triangle, in any triangle, not just a right triangle? Michael?
180.
Yeah, they all add up to 180. So if you've already used up 90 for the right angle, then that means all you have left is 90 for the other two. And they would have to be acute because if they weren't, you'd go over 180 when you add them all up. Okay, so they all have to add up to 180 degrees. Very easy to prove that they have to add up to 180 degrees. That's a proof from geometry. Not really something we're going to look at here. Okay, but they do add up to 180. All right, there's a theorem that we can use that tells us a relationship between all the sides. It's a theorem that does apply to right triangles, and it's the Pythagorean theorem. Can anyone tell me what that theorem is? Mabel?
A squared plus B squared equals C squared.
Okay, A squared plus B squared equals C squared. And we're going to take a look at why that's true in a second. But can you explain to me, what does that mean? Like, what do you mean when you give me an A, a B, and a C? What's the A, the B, and the C?
It's both the legs squared added together, and that equals the hypotenuse squared.
Yeah, so when you take a leg and square it, take the other leg and square it, add them up, that will equal the hypotenuse squared. Right? And this is easy enough to show why, and that's a triangle-related formula, and we're doing trig, which is all about triangles, so let's see why that's true. All right, so let's take a look at that diagram. Think about it. Okay, so in this diagram, okay, what I've kind of set up here is we have a big square on the outside, and then we have another square on the inside, and the square on the inside is it's almost like it's turned a little bit. Now, we have several different kind of shapes going on here. We've got the big square, we've got the smaller square on the inside, and then we've got these triangles that are on the outside of that smaller square. And all the triangles are congruent. Okay, they all have sides of A, B, and C. And what I want to do is I want to find the area of the inner square, but I want to do it two different ways. All right. So, what's the formula for the area of a square? Does Sophie?
Length times width.
Yeah, length times width, or just the side squared, because the sides are the same. So can somebody give me a formula for the area of this square? And I'll just do it in green, so you know exactly what I'm talking about. Okay, what's a simple way you could find the area of that square? Okay?
C squared.
C squared, yep. So I'm just going to put the area of the green square, that's what that symbol means, equals C squared. Now I want to think about another way I could find it. Think about a different way that I could find the area of that square. Anybody give me, you don't have to give me a formula, I'm just looking for an idea. Like you could do this, and then that could give you the area as well. Yep, Tim?
You find the hypotenuse through through one of those triangles, and that's one of the sides, and then you just square that. Because they make triangles of A, B, and C. If we can find the hypotenuse, then C would be the hypotenuse.
Well, we're not going to have any numbers, so we're not going to be able to like find the hypotenuse like as a number. Is that what you meant?
I think so.
Okay. I'm thinking of something a little different. It is going to involve the triangles, though. Definitely going to involve the triangles and the bigger square, too. Yeah?
You can find the area of the big square,
Yeah?
and then the area of the one triangle, and then multiply the triangle by 4 and subtract it from the total area.
Exactly. So we're going to let's start with finding the area of that big square. What's the length of one side of the big square, the blue square? Length?
A plus B.
A plus B. Remember what we said about area of a square. It's just the length of a side squared. So there's the area of the blue square. And now, let's find the area of, I'm just writing down some different formulas. Let's find the area of one of these triangles. All right, so let's find area of the red triangle. What's the formula for the area of a triangle?
1/2 base times.
Yeah, 1/2 base times height. So in this case, we could have 1/2. What's my base? Oh, either way, yeah, 1/2, and my base you said was A. Then what would my height be?
B.
B. All right, so it's 1/2 A times B. Okay, so now we've got a few formulas. Now let's do the idea that Mabel said. So can you tell me again, Mabel, what you said to do to find the area of, so we'll call this the first way to do it, and let's call this the second way. And I'm just going to write down the idea that you said. Go ahead.
So it would be the area of the blue square
So area of blue square, yeah,
minus 4 times the area of this triangles.
yeah. So if we take the area of the blue square, that's the big blue square, and subtract all 4 of the triangles around the edges, then we would just be left with the green square in the middle. And that would be the second way we could find the area. So let's do that out. So the area of the blue, okay, we need to square that. So we're going to have a squared plus 2ab plus b squared. Remember, you have to FOIL that out. That's the blue. Minus 4 times the area of the red triangle. So 4 times 1/2 AB. Okay, let's combine some like terms here and see what happens. So a squared plus 2ab plus b squared. What's 4 times 1/2 AB? Yep.
2.
2, just 2?
Oh, 8. Oh, wow. No, just the 2 and 4AB.
2 times 4ab?
Oh, so no. I'm thinking, I'm sorry, that would be 2AB.
2ab, yep. All right, and what's going to happen there? Yeah, what cancels out?
280.
Yeah, the 2ab plus 2ab minus 2ab. So we have a squared plus b squared. All right, so that's the second method for finding the area of the green square. And this was the first method. Now, what do we know about the first method to find the area and the second method if we compare the results? Yeah?
Equals each other.
They should be equal to each other, right? These two methods should be the same. So the first method should equal the second method because it's the same green square. We just found an area of the square two different ways. So let's take what we got in method 1, which was c squared, and set it equal to what we got in method 2. And there you go. So there's the Pythagorean theorem, and there's the proof. There's probably 50 different ways you can prove that formula. This is one that's a more visual way, and it uses geometry to do it. And look at the labels that we use. So if you have a triangle, like focus on the red one now. A and B would be your legs, and C would be the hypotenuse of that triangle. So as long as you use those letters to name your sides, then this formula will always work. Okay, if you switch what you call the A, the B, and the C, well, then it wouldn't work. But we always let the A and the B be the two legs, and the C is always across from the 90. Okay, so any question on that? So it was a pretty straightforward proof of Pythagorean theorem. All right. So that theorem we're going to use when we're solving triangles, especially when we want to find out something about the sides. What I'm going to do now is I'm going to give you guys the 6 trig functions that we had last week. Sine, cosine, tangent, cosecant, secant, and cotangent. Except now I'm not going to define them in terms of a coordinate. Okay, last week we defined them as y, x, y over x. And that's when we were doing unit circle trig. What we're going to define them as now is sides in a triangle, okay, knowing different sides. I'm going to talk about what the sides mean, but let me give you the definitions first, and then I'll explain the terms if you're not sure what they mean. So all the trig functions are what we call ratios. They're all ratios of two lengths. Sine is the length of the opposite side divided by the length of the hypotenuse. Cosine is the length of an adjacent side divided by the hypotenuse. And tangent is the length of the opposite side divided by the length of the adjacent side. Now, does anyone remember, once we had the 3 on the left, what did we do to each one of those to get the 3 on the right? Yep. Yeah, took the reciprocal. Okay, so if I take the reciprocal, Julie, what would be the reciprocal of sine?
Hypotenuse over opposite.
And there's your cosecant. Mabel, what would be the reciprocal of cosine?
Hypotenuse over adjacent.
And there's your secant. And Tim, what would be the reciprocal of cotangent?
Adjacent over opposite.
Yep. Adjacent over opposite. So really, once you know the 3 on the left, you automatically know the 3 on the right. Okay, just by flipping. So now, what do I mean when I use these terms? Well, I think hypotenuse is pretty clear. Okay, hypotenuse is the side that's always across from the 90 when you're working with a triangle. But the other two terms, opposite and adjacent, are what we call relative terms. Another example of relative terms are left and right. Left and right are not always the same thing for everybody. It kind of depends on which way you're facing. So for me, left is the door, but for you, right is the door, because we're facing different directions. Well, opposite and adjacent, it's the same idea. They'll always tell you in the triangle which way you are facing, and then that determines what side is opposite and what side is adjacent. The way they tell you which way to face is they'll mark an angle. They'll say, like for your reference point in this angle, they'll say, like, pretend you're standing at theta. Well, hypotenuse is always across from the 90. And opposite is always the side that is farthest away from your angle. Okay, opposite is always the side that is farthest away from your angle. It's the side that if you erased it, it has no effect on your angle at all. You still have an angle right there. To have an angle, you have to have two sides, or two rays. And you do. Okay? If you get rid of the opposite side, no effect on the angle. Adjacent is the side that is right next to the angle, but not the hypotenuse. Okay, so adjacent is the side that is right next to the angle, but it's not the hypotenuse. Adjacent is the side that if you erase it like this, you don't have an angle there anymore. You just erased one side of your angle, now it's just open. You got rid of your angle. Now, if you take the same triangle and switch your perspective, it's kind of like switching which way you face in a room. Now left and right will change. Let's say you're doing everything from the perspective of theta, and now they're going to label the top angle as theta. Well, no effect on the hypotenuse. But again, opposite would be the side that's furthest away, and adjacent is the side that's next to the angle, but not the hypotenuse. So any question on that idea about opposite and adjacent being relative to the angle in the triangle? Okay, so if you had a triangle, let's say we had one like this and we labeled it in two different angles, alpha, beta, and you said to me, find the sine of that triangle. Well, I can't do that. That's a vague question. It's like having three cars to pick from and somebody says, buy the car. Wait, which one? There's three. Which one do you want me to take? So if you said to me, find the sine of this triangle, I'd say, well, which angle do you want me to use? Do you want me to find the sine of alpha? Or do you want the sine of beta? And that would change my answer. Usually those are numbers, but we'll practice with letters as well. All right, so one thing that doesn't matter when you're doing trig and you're finding sine, cosine, and tangent is if you use triangles that are similar, you're going to get the same answers. And similar means one triangle is a larger version than the other. So like if I said to you, draw a 30, 60, 90 and find the sine of 30, you might say, well, how big should I make my triangle? How big should the sides be? It doesn't matter. If you make one 30, you make one angle 60, and you make one angle 90, and somebody makes a triangle 5 times the size, you're each going to get the same answer. So if you have two right triangles, and the angles are congruent, then that automatically means the triangles are similar. Remember, similar from geometry means one is a larger or smaller version than the other proportionally. Okay? So you put something on a photocopy machine and hitting 50%. It makes a proportional copy that's half scale. So the previous trig functions that we just defined will always have the same value for any angle. It doesn't matter if you have a 20-degree angle in a really tiny triangle or a 20-degree angle in a ginormous triangle. If you do the sine of 20 degrees, it's always the same. Doesn't matter the size of the triangle. So let's look at an example. Here's two 30, 60, 90 triangles. One of them is twice as large as the other. But these are to scale. Okay, the sides are correctly labeled. And you can check with Pythagorean theorem. A squared plus b squared does equal c squared. It all works. Well, let's find the sine of 30. And let's do it in the triangle on the left. Sophie, what was the formula for sine again?
Opposite over hypotenuse.
And what side is opposite the 30 in this case?
1.
1. And what's the hypotenuse?
2.
2. So in the smaller triangle, the sine of 30 is 1/2. Now let's take the same triangle, bigger version. Let's find the sine of 30 over here. Still opposite over hypotenuse. So Maddie, what's opposite the 30 degrees?
2.
2. And what's the hypotenuse?
4.
And what does that reduce to?
1/2.
1/2. So again, that's the point. The sine of 30 degrees is always the same. Doesn't matter how big or small of a triangle you make with a 30 degree. Any question on that idea? So it gives you a lot of flexibility. If I said to you, find the cosine of, say, 60 degrees, as long as you know how to sketch a triangle properly and label the sides correctly that has a 60-degree angle, you could find the cosine of 60. And that would be one we should know how to do from unit circle trig. We talked about the numbers root 3 over 2 and 1/2. So we do know how to sketch a proper 60-degree, 30, 60, 90 triangle from unit circle. In that case, the hypotenuse would be 1. It doesn't matter. Okay, it can be any size you want. You just have to label the sides correctly. All right, so how do you find all 6 trig functions if I give you one of them? Okay, like let's say I gave you the sine. Okay, I'm telling you I've got an angle. Here's the sine. Find the other 5. Well, actually, before I show you how to do it, anybody have a guess what you would do? Mabel?
Would you, well, 5 would be the opposite and 6 would be the hypotenuse. So you put that into the Pythagorean theorem.
All right, so yeah, what we would do here is we'd want to make a sketch, right? Put theta in the diagram. So here's the triangle. Again, we'll do this in a second. I'm just kind of writing down what she said, and I want to give you the directions first. But you can put theta wherever you want. She said 5 is the opposite. She said 6 is the hypotenuse. And now all we have to do is use Pythagorean theorem. We can get the third side, and then we have opposite, adjacent, and hypotenuse. And we're good. We can do all 6. Okay, so let's kind of write down what we just did. So take the trig function that you're given and use it to label 2 sides of the triangle. So we were given sine. So in your head, you should think, okay, what did they give me? Sine is opposite over hypotenuse. Okay, those are the 2 sides they gave me. So label those 2 sides, and then use Pythagorean theorem to find the third side. Now you have all the sides, and you can find any trig function you want. You just needed that third side. But that's the idea of the example that we're going to do. Okay, any question on that idea? Now, the only thing is, when we use Pythagorean theorem for these kinds of problems, generally we don't want to use decimals. So that means a lot of times we're going to end up with a square root as one of the sides. And if that happens, fine. We'll just simplify it as much as we can. So that means 2 things. 1, don't leave an answer like this. Square root of 20 could be simplified. Can someone tell me what that simplifies to? Yep.
2 squared is 5.
2 squared is 5. So make sure you simplify things like that. And the other thing that can happen that we don't want with square roots, happen with unit circle trig, is what? You don't want to have a square root, yeah?
On the bottom.
Yeah, we don't want to have a square root in the bottom. So if you had an answer like that, how do you fix it so your square root isn't in the bottom? Yep.
Multiply both times 5 by square root
multiply top and bottom by square root 2. And that's what we'd be looking for a final answer. Okay, so no decimals. Make sure you simplify square roots as much as you can, and make sure you rationalize any fractions. Don't leave square roots in the bottom. Rationalize the denominator. All right. Okay, so we kind of already set this one up. We drew our triangle. Put theta in. It doesn't matter if you put theta in the bottom or you put it in the top. We just have to put theta somewhere. And then wherever you put theta, make sure the opposite side is 5 and the hypotenuse is 6. All right, so Lindsay, temporarily, what could I call this side? I'm thinking of something I can name it so I can start to do Pythagorean theorem.
A.
All right, let's call it A. And Madison, could you set up Pythagorean theorem for me using this diagram?
A squared plus 5 squared equals 6 squared.
Okay. So A squared plus 5 squared equals 6 squared. And Caleb, can you give me the first step to do that out?
Simplify by squaring both 5 and 6.
All right, and what do you get when you square 5?
25.
Yep, and 36. Okay, Sophie, my next step.
Subtract 25.
Subtract 25. That's gone. How about Annalise? What do I get from that?
A squared equals 36.
A squared equals
11.
11. And Nick, my last step to get A by itself?
Square root both sides.
Square root both sides. And remember, we don't want to take the square root. We want to leave that as a decimal. Unless they say not to. Then we can do a decimal. But most of the time, in a problem like that, we're going to leave it just like that. Okay, questions on that? Now, find all the trig functions. So the sine, we already knew, was 5, 6. What's my cosine? Yep. Square root of 11 over 6. And how about Tim, my tangent?
Your tangent's going to be 5 over square root 11.
So it would be 5 over square root 11, and when you fix it?
It's going to be 5 square root 11 over 11.
Yep. So there's my sine, my cosine, my tangent. Now, so what I'm going to do is just move this so I got more space. Make it smaller. There. Okay, and now, Julie, what am I going to do with those 3 to get the next 3?
The reciprocal.
Yep. And do you remember the name of the reciprocal for sine?
Cosecant.
Cosecant. Okay, so Caleb, what's my cosecant?
6 over 5.
6 over 5. And Madison, how about the name of cosine? When you flip it? Secant? Okay. And Sophie, if I flip that, can you tell me what I get and fix it?
6 squared 11 over 11.
6 squared 11 over 11. Good. And the last one, Maddie, what do I get for the name when I flip the tangent?
Cotangent.
I get the cotangent. I should be putting the theta in here. I forgot it on the first 2 over here. So the cotangent of theta on Lindsay will equal,
Square root 11 over 5.
yep, I would just go back to the first one we had, because if you flip it, square root goes to the top, and you're done. Any questions on that? All right, so let's do this one. I think this one you'll see is actually a little nicer for answers. Does anyone know what the hypotenuse is going to be in that one? Yep.
13?
Yep, it is 13.
All freshmen, thank you.
Okay, so that is 13. And whenever all the sides in a right triangle come out without any decimals, they all come out to integers. There's a special name for that. 3, 4, 5 is another one. There's infinitely many of these things. Does anybody know what that's called? That's called a Pythagorean triple. So anytime you have 3 sides that don't come out with any decimals in a right triangle, those 3 numbers form what we call a Pythagorean triple. And if you look online, there's all kinds of stuff about Pythagorean triples, like how you can generate them. Like 3, 4, 5 is one, 5, 12, 13 is another. There's infinitely many. How do you come up with more of them? Well, there's a way to do it. We're not really super interested in doing that. We're just finding the 6 trig functions. And what's nice about Pythagorean triples is you don't have any roots. So you're never going to have to worry about simplifying something that ends up in the denominator. All right, so let's start with the sine, cosine, and tangent. All right, so Tim, what's my sine here?
Your sine is going to be 5 over 13.
Yep, 5 over 13. Michael, my cosine?
13 over, oh, never mind, sorry, it's going to be 12 over 13.
Yep, 12 over 13. And Julie, my tangent?
5 over 12.
5 over 12. And is there any question on how you would do the cosecant, the secant, or the cotangent? Now, just to be clear about what we're doing here, you are not finding the angle. I still have no idea how big that angle is. I know some different things about it. I know the sine of it, I know the cosine of it, and I know the tangent of it. And knowing those pieces of information, in fact, just knowing any one of those pieces of information, is enough to tell me how big that angle is if I wanted to find it. Right? So there will be some problems on the test where that's all you have to do. Find the sine, the cosine, or the tangent. And people confuse that with actually finding the angle itself, which is different. Questions on what I just said? Okay, I don't think today we're going to actually get into finding the angle. That's why I didn't get the calculators out, but that'll probably be tomorrow. We'll see. All right, so let's find the 6 trig functions of 45 degrees. Now, it's up to you to figure out how to label the sides. Does it matter how big or small you make that triangle? No. We learned that it doesn't matter as long as you properly label the sides, the trig function. Okay, so now, again, as I was saying, you have to figure out what to label these sides as. I would pick numbers that are easy to work with, but there's infinitely many 45, 45, 90 triangles. So, can somebody give me a suggestion on how to start labeling these sides? Can't really go wrong with just labeling one side to start, unless you pick a negative number. Yep.
You could do A or B.
Okay, we could do the 2 legs. Before we pick a number for them, what do we know about how A and B compare to each other?
They're equal.
They're equal. That's isosceles. So, let's label those 2 legs. How long do we want to make the legs? Yeah?
32.
How about 4? Or
There's
5?
4.
Okay, we could use 4. You could use 32 as well, but if you use 4, that's fine. You could have gone even smaller. But 4 is okay. Now, let's solve for the hypotenuse. What's 4 squared? 16. Plus, what's 4 squared? 16. And that's equal to the hypotenuse squared. So, square root of 32. How does that simplify?
2 square root.
Yeah?
2 square root 4.
Let's see. So we break that up into 16 times 2 What did you say?
I said 2 square root of 4, but it's like.
That would be 4 then, yeah. 2 square root of 4 would be 2 times 2, which would be 4. Yep.
2 square root 8.
But square root of 8 can be simplified again. We gotta simplify it as much as we
Four
can.
square root 2.
4 square roots of 2. Alright, so the way I think of this is I think of it as 16 times 2. When you multiply the square roots together, you can separate it into 2 roots. And now the square root of 16 is 4 square roots of 2. Okay, so we have a hypotenuse of 4 square roots of 2. And Nick, what's the formula for... Oh, they want us to do all 6. Okay. So let's start with sine, cosine, and tan. Now, what I would probably do, because I noticed something here to make these numbers easier right away, and this would have happened if you had picked smaller numbers instead of 4 and 4, but it's okay. Does anybody notice what I could do to all 4 of these sides? Yeah?
You divide them by 4.
I could scale them all down by 1/4. Right? And then it's just going to make all the numbers smaller. So if I divide by 4, I get 1. Divide by 4, I get 1. Divide by 4, I just get square root of 2. So originally, I probably would have picked 1 and 1 for the 2 legs. But we did it now, so I think it'll make the numbers a little easier. And if you had picked 1 and 1, you wouldn't have had to deal with all this stuff right here. All right. Now, we're doing 45 degrees, so everything has to be from the perspective of a 45-degree angle. Does it matter which one? No, because the sides opposite them are the same, so no matter which angle you use as your point of reference, you're going to get the same answers. Let's use that one. All right, so Caleb, what would the sine of 45 be?
It would be square root of 2 over 2.
Yep, I'm just going to break it into 2 steps for people that don't see it. You start with 1 over the square root of 2, and then when you fix it, it's square root of 2 over 2. Again, these should look really familiar because we did these with unit circle already. How about Madison, what's my cosine?
1 over square root 2 over 2. Square root 2.
Yeah, it's going to be the same thing because the opposite and adjacent are the same. And because the opposite and adjacent are the same, when you divide them, what do you get? 1. All right, let's practice the other 3. Cosecant of 45 degrees. Let's put this up here. Okay, what is the cosecant?
Square root.
Yep, just take what we had and flip it, square root of 2. Because it's isosceles, that means the secant is also square root of 2. And Annalise, what about my cotangent?
That'd just be 1.
That's going to be 1. Okay, any questions on those? So if you're asked to find the trig functions of a 45-degree angle, as long as you use any 2 sides for the legs that are the same, you can use Pythagorean theorem and get your hypotenuse. All right, let's take a look at finding the 6 trig functions of a 60-degree angle. So if you think about a 60-degree angle, you think about, you have to make a right triangle that would have a 60-degree angle in it. Well, what does that mean the other angle is going to be? If you have a right triangle and it already has a 60, the other one is going to have a 30. So the way I think about it is I start with an equilateral. And you could let the sides be anything you want, but I remember that in a 30, 60, 90 right triangle, one side is automatically half of the other. So if I pick a number that's even for one of the legs, then the other side will come out nice because I'll be able to divide it by 2. You don't have to. If you pick like 1, then the other side would be 0.5. You can deal with the 0.5 if you want. But this is what I would do. Let's start with an equilateral triangle where all the sides are 2. How could I make a 30, 60, 90? out of that. What I have to do to make a 30, 60, 90. So
You multiply all the sides by 2, you get double it, one side.
well, right now we have an equilateral triangle, right? So I need to construct a 30, 60, 90 out of that. Because right now I have a triangle that's 60, 60, 60. But I have to modify that picture. I want to keep everything that's there, but I have to modify it by adding something. How can I modify that equilateral so it turns into a 30, 60, 90? Tim?
Double one of the sides.
Well, if I double one of the sides, then I'm going to have an equilateral that's 4, 4, and 4. I have to add to the picture. Yep.
From like the bottom right corner, draw a line that goes horizontally until it's like halfway through the left side.
So from, and since it's equilateral, it doesn't really matter which corner you pick. So what did you say? Pick any angle.
Bottom right.
Yeah.
And then draw horizontal, like a straight line left until it goes halfway through the left side.
Yeah, and what I'm going to do is I'm going to use the top one because then I can make it perfectly vertical, and the computer can make things perfectly vertical and horizontal. At an angle, I would have to guess what it's exactly halfway, but since it's a vertical, it'll automatically put it right there for me. Okay, now what do we know about what I just drew? What did that just do to the triangle? Yeah?
Split it in half.
It did split it in half, and the way we know that it split it in half is prove that the triangle on the left and the right are congruent. Well, we know this side is equal to this side. That's a definite. We know this side is equal to itself. That's the reflexive property. And we know that these are both 90s. So I think from geometry there's a theorem called the hypotenuse leg theorem that says if the hypotenuse and two right triangles are equal and they share a leg, then the two triangles are congruent. Hypotenuse leg theorem. So we know by the HL theorem, these are congruent, which means this side is congruent to this side. And if it's a total length of 2, then they each must be a length of 1. Now we have two sides labeled. Third side is easy with Pythagoras theorem. All right. So let's just get rid of the extra marks. So now we know this side is a 1. And because the two triangles are congruent, that also means that the angles right here have to be congruent. You started with a 60, and because they're congruent, they each must be 30. So here's your 30, here's your 60. And how would I get the length of that last side right there? Tim?
Pythagorean theorem.
Yeah, let's just call this A. And A, if you just trust me with Pythagorean theorem, it will come out to square root of 3. Because if you square root of 3, you get 3. And if you square 1, you get 1. 3 plus 1 is 4. Take the square root, get a hypotenuse of 2. Okay, so now we know A is the square root of 3. Now they want to find the 6 trig functions of 30 and 60. Alright, so let's take, I have, perfect, let's do the 30s. So do all the 30s. Alright, we'll start with the sine of 30. Julie, what's the sine of 30?
1 over 2.
Yep, 1 over 2. And Caleb, cosine of 30?
That would be
Thank you.
Welcome, Merry Christmas.
Oh, thanks, Dan. Yeah. Go ahead, Caleb. What?
Square root of 3 over 2.
So let's see. It's 30 adjacent over hypotenuse, square root of 3 over 2. Perfect. And the tangent, Madison?
1/2 over, so 1 over square root of 2, which is simplified square root of 3 over 3.
Yep, it would be 1 over the square root of 3, which then simplifies to square root of 3 over 3. Okay, Sophie, my cosecant? 2. Maddie, my secant?
2 square root of 3 over 3.
Yep. So 2 square root of 3 over 3. And Lindsay, my cotangent.
Square root of 3.
Yeah, when you flip it, it would be 3 over root 3, and when you fix it, it would just be root 3. Now, to do the 6 trig functions of 60, it really would be all the same answers again, except what's happening is they're all going to really switch places. Does anybody want to see the ones for 60? It's just everything that was opposite becomes adjacent, and everything that's adjacent becomes opposite. They just switch. Okay, so there's our 6 trig functions of 30. And, okay, last thing. So, 2 acute angles are complementary if what? Yep.
It's a right triangle. And then 9.
Well, we're going to touch on that in a second, but even not thinking about a triangle, just in general, two angles are complementary if, and they have to be acute angles, because, for example, if I said what's complementary with 105 degrees, nothing. So they have to be smaller than 90. Yep.
They add 90.
Yep, 2 acute angles add up to 90 degrees. That's called complementary. Now, how come the 2 acute angles in a right triangle are always going to be complementary? I think we already kind of talked about that, but yeah.
Because the right angle is 90, and then there's only 2 sides left, so it has to be less than 90. Like, they add up to 180.
All right, so yeah, they all have to add up to 180, and if you use up 90 for the right angle, that leaves 90 for the other 2. So if the other 2 are add up to 90, then they have to be complementary. All right. So let's look at how we're going to label triangles in general. Anytime we have to label a triangle and we don't know its sides and its angles, that's how we will label it. You can draw it if you want to have it facing like a different way, and that's fine. The important thing is, wherever you put A, alpha has to be the angle across from it. This is to keep track of things. A will always be across from alpha, B will always be across from beta, and C will always be the hypotenuse. Again, can you label it different ways? Yes. Well, but this is to help you kind of keep track of things. Now, what's a little confusing is our book uses capital letters for angles and lowercase letters for sides. I don't like doing it that way because then it can be confusing. For example, if you ask me, how did you get B? I'd have to say, well, which B? The capital B or the lowercase b? And then certain letters even can look the same. So if you decided to use different letters to label things like let's say you made C one of the legs, which I would never do. But if you did, and then you said, oh, well, the angle across from it, our book uses C, well, now you'd have a capital C and a lowercase c, and that's a mess, because now it's hard to tell which one is which. So the simple way to get around that, we'll always use English letters for the sides, Greek letters for the angles. A across from alpha, B across from beta. All right, so let's take a look at this triangle, and let's find a couple things about it. Let's start with the sine of alpha. What would the sine of alpha be in that triangle? Caleb?
B over C.
That would be the cosine.
Oh, A over C.
A over C. Okay, so So we got A over C. Now, I'm going to do two things. Instead of sine, I'm going to put the word co in front of it. So I'm going to find the cosine. And instead of using alpha, I'm going to use the angle that's complementary to alpha. In that diagram, what angle is the complement to alpha? Yep.
Beta.
Beta. Okay, so we did two things. We put the word co in front of the trig function, and that gave me cosine, and I'm using the complement of the angle I started with. And now, let's find that. What's the cosine of beta? Tim?
A over C.
It's A over C again. They came out exactly the same. Okay, let's do another one. Let's do tangent of alpha. What's the tangent of alpha in this case? Yeah, maybe.
A over B.
A over B. Now, let's do another problem, but let's make a very specific problem. Let's put the word co in front of this. So let's do the cotangent. And instead of using alpha, let's use the angle that is complementary to it. Beta. What's the cotangent of beta? Cotangent is adjacent over opposite. Yep. It's A over B again. And this pattern would always continue. There's always two things in the triangle that come out exactly the same. And the pattern is, whatever function you started with, put the word co in front of it, and that's called a co-function. Okay. So actually, let me write these down. So co-functions. There's three pairs of them. Sine, and put the word co in front of it. Cosine. Sine, cosine. The next pair is secant, and then put the word co in front of it. Cosecant. And then the last pair is tangent, and put the word co in front of it. Cotangent. Sine, cosine. Secant, cosecant. Tangent, cotangent. Those are the three pairs of what we call co-functions. So if you have co-functions of angles that are complementary to each other, the answers always come out the same. And that's called the complementary angle theorem. Co-functions of complementary angles are equal. They always come out the same. So, for example, what's the co-function of something? Oh, that's cosine. And what's the angle that's complementary to 20? How much? 70. Those are co-functions. Those are complementary. Therefore, they would come out exactly the same. I don't know what they would come out to because that's not an easy one to do in my head. But whatever the one on the left comes out to, the one on the right would be exactly the same. Any question on that idea? So where that comes in helpful is a problem like this. The sine of 35 minus the cosine of 55. What I'd be more interested in this kind of problem is not really the answer, because you could just type that in on a calculator. I'm more interested in you explaining why you get what you get. So anyone tell me what would happen here? Caleb?
Would equal 0,
That's 0. How come?
because the angles are both complementary and sine and cosine are co-functions of one another.
Yep.
So then it would just be subtracting from itself as sine 35 is equal to cosine 55.
Yeah, these two things are equal. Sine and cosine are co-functions. 35 and 55 are complementary. So you are subtracting two things that are the same. And it doesn't matter what you subtract two things that are the same, the answer is always 0. Now, how about if you add two things that are the same? Like if I put a plus sign in here, if you add two things that are the same, do you always get the same answer? No, you get that thing doubled. So we still wouldn't know what that would be, but subtracting, you can do it. What other operation do you think a trick like this would work with? Works with subtraction, doesn't work with addition. There's another one it would work with. Madison?
Division.
Yeah, it would work with division. So in this case, again, it has to be set up very special. If you change that 20 to like a 21, well, now it's messed up. Can't do it without a calculator. But what's this going to come out to? 1. Tangent, cotangent. Those are co-functions. 20 and 70 are complementary. By our theorem, the top is equal to the bottom. When you divide two things that are the same, you get 1. How about when you multiply two things that are the same? What do you get? Nick?
Squared.
Yeah, you get the original thing squared, which could be different depending on what the original thing was. So that trick wouldn't work for multiplication. But it does work for division and subtraction. Okay. Any questions on that? All right, so that's the first part of 6.5, part 1. Okay, we've got about 11 or 12 minutes left. So if you have any questions, if you want to start that, you can. But now would be a good time to check in with me if there's anything you need to talk about. Most of it's in the book. 1 to 14, 16 to 20 even. 21 to 24, and then simplify these two problems. Basically just like what we did at the end. And the problems from the book are on page 361. Tomorrow we'll finish 6.5, and remember Wednesday we'll have our test on the one section.